Environmental Engineering Graduate Seminar today. Today we're honored to have Andy Erickson, who's at St. Anthony Falls Lab at the University of Minnesota. Andy is an alumni of our department, so that's great. He's a research associate at St. Anthony Falls, registered professional engineer working on projects related to understanding water quality in urban and agricultural watersheds, assessment and maintenance of stormwater treatment practices, developing new stormwater treatment technologies. He's a lead author on the book entitled Optimizing Stormwater Treatment Practices, a Handbook of Assessment and Maintenance. He's the editor of the University of Minnesota Stormwater Newsletter Updates. And he's also the coordinator for the Minnesota Stormwater Seminar Series and maintains the St. Anthony Falls Laboratory Stormwater Research website. He has co-authored several journal articles, conference proceedings, and project reports. In addition, he provides consulting services for TMDLs, lake management plans, watershed district projects and regulations, and water quality modeling. So that's great. So Andy, take it away, and we can have questions at the end. So thanks very much.
Sounds good. Very good. Thank you for that introduction, Professor Bruckdahl. Hello and welcome. Again, my name is Andy Erickson, and today I'm going to talk about urban stormwater runoff research, specifically how we're innovating practice to improve water quality. And so I'm going to talk about actually 3 different projects. We'll get into a little bit of detail on each one because I want to demonstrate that we're working on a lot of different things in this stormwater runoff research area. To start though, I want to make sure we're all on the same page and we're understanding the same context. And if we look at a traditional stormwater runoff management model, this is what we see in our urban landscapes. We see houses with rooftops, we see sidewalks, driveways, roadways, curbs and gutters. And what this is all designed to do is in our urban landscape to collect and capture and convey rainfall and get it away from our urban infrastructure. So all of these impervious surfaces, the rooftops, the driveways, the sidewalks, the roads and curbs and gutters, reduce how much water can soak into the ground. And they increase the volume of runoff, the water that runs off of these surfaces. And so we collect them and we convey them typically into curbs and gutters and into drain pipes, which goes into an underground stormwater management system, which essentially centralizes that and discharges it typically back to surface waters. So our lakes and our streams and our rivers. And in that, we can create problems. Many of the effects of urban stormwater runoff is polluted surface waters. And whether that's the Great Lakes, such as Lake Erie here, who gets a lot of phosphorus and has many algae blooms, we see that across the United States and around the world where we have too much phosphorus in the water. When we talk about just the US, as of 2016, we had just under 3,000 water bodies that were identified as impaired due to having too much phosphorus. And impaired simply means too much of a certain pollutant. It's above water quality standards. So we implement total maximum daily loads, or TMDLs, to address those impaired water bodies and reduce the loads and improve water quality. And in many of the TMDLs for these impaired water bodies in the US, they are calling for often large phosphate load reductions on the order of 60% load reduction or 80% load reduction of the amount of phosphorus we deliver to these water bodies. And a leading contribution of that phosphorus in many of these locations now is urban and agricultural stormwater or rain-driven runoff. And so it's a big issue in Minnesota, in Michigan, and across the US and around the world. So what is in urban stormwater besides things like phosphate that we see impairments for? There are solids, inorganic and organic solids. We see things like sand and grit and rocks, inorganic materials. We see litter and debris as inorganic materials. We also see organic solids, such as leaves and grass clippings and other organic material. A lot of that organic material can also contain nutrients, such as phosphorus and nitrogen. And that can be both in the particulate phase, if it's associated with organic material, but also can be in the dissolved phase, which we'll talk about in a few slides. We also see metals, typically coming from our vehicles, as tires wear down and brake pads wear down as we drive our vehicles across the urban landscape. That can contribute metals to the roadways, which then gets washed off and enters our storm sewer collection system. Our vehicles can also contribute hydrocarbons in terms of exhaust and other materials. In cold climates, such as in Minnesota, we also find de-icing agents. We see chloride, from sodium chloride, magnesium chloride, even calcium chloride salts that are used in our de-icing and anti-icing reagents. However, we are seeing changes in the de-icing and anti-icing management practices to where we're now seeing new chemicals, such as acetates, that we have to think about and how that affects our water bodies as a result of transportation through our stormwater management systems. And of course, because the storm sewer system and the urban landscape is in the environment, it's outdoors, there are bacteria and pathogens. And that's just a natural occurrence. But the question for stormwater managers such as myself is, how does our system, how does our pipes, our collection system, our conveyance, all the junctions, perhaps exacerbating that problem, creating situations where bacteria and pathogens in this case can grow exponentially and cause beach closings and impacts into our water quality. And of course, we've done other research on other pollutants, things like PFAS and PFAS, other chemicals that we see in stormwater management where we might not even expect them to be there. And now the challenge is, where are they coming from? How are they getting into the system? And then how do we treat them? So I mentioned on the previous slide that we have both solids and dissolved. And it can be easy to think, if we capture the solids, if we capture the sediment, if we settle that out, if we filter it out, we can go a long way to reducing pollution. And that's true. But if we ignore the dissolved component, we can actually miss a big fraction. And this slide is showing actually nationwide data from the United States, looking at runoff from a variety of different land uses and climates, and showing the total concentration for the various pollutants on the left or vertical sides of the graph. In blue is the total concentration of those pollutants. In red, compared to the blue, is the dissolved or the soluble fraction for those same pollutants. And on the right side, you can see I've calculated the dissolved fraction. And we can see for many of these pollutants, 45 to 50% of the total concentration, regardless of the range and regardless of the pollutant itself, are dissolved forms. Now, some pollutants, chromium and lead, have a lower dissolved fraction, and that's just based on the water chemistry. We understand that they partition to particles more readily, so we're going to see lower concentrations in the dissolved phase. But if we went on the assumption that we need to remove the particles, we would really only get halfway there to solving our problem. So we need practices that are robust enough to capture both the soluble and the particulate phase of these pollutants. So not only do we have a lot of pollutants, we have now two different phases we need to deal with. But what's also interesting about this stormwater runoff is that it's highly variable. This is looking at just one pollutant. This is just phosphorus. On the lower graph in this slide, I have on the left side the concentration of total phosphorus in milligrams per liter. And on the right side, I have the total phosphorus load in kilograms per event. Now, this is monitoring data, pretty detailed monitoring data that happened to be done in the Twin Cities metropolitan area of Minnesota. And if you look at that data, you can see for all of these different events, there were some events in which the dissolved fraction was very low, between 0 and 10%, maybe on the order of 3 or 4 or 5% dissolved. But there were also several events that were 100% dissolved fraction. And that's because the nature of these pollutants in the watershed will vary based on the time of year, based on the watershed itself, based on the location within the management system. Are you up in the watershed near where water and runoff is generated, or are you at the bottom of the watershed where that has now been concentrated and is being discharged to the surface waters? The top part of this graph is just a histogram showing kind of the relative distribution. And we have good distribution across the entire range, but on average, if we calculated an average for all of this, it'd be about 45%, which corresponds to the median values that we saw on the previous slide. So we have a lot of variables. We have not only a lot of pollutants, we have multiple phases. We also have variability in those phases and those pollutants over time and with space. So this is a complex problem that we have to deal with. But on top of that, it's also changing within the system as it's moving. It's a dynamic system. We have large particles breaking down into small particles, solids dissolving into soluble and vice versa. We have ions detaching and attaching to soil particles or other solid surfaces. We have degradation, both biodegradation and natural degradation. And we have aggregation, or biological processes that are consuming some of our soluble ions or converting them to something else. So we have a very dynamic, highly variable, ever-changing system. It's a moving target that we have to hit when we're trying to treat stormwater runoff. But we know that these pollutants have a negative impact on water quality. Nutrients can cause eutrophication, which is essentially a biological overproduction in our lakes. I like to use the analogy that in these freshwater systems, temperate freshwater systems like we have in Minnesota, the phosphorus is like sugar for the algae. If you put too much sugar in a lake, it's like a sugar rush and the algae go crazy and you have giant algal blooms. So that's eutrophication. Metals, we can have bioaccumulation and toxicity issues. Again, in other parts of the country, metals such as copper are a big impact to certain ecosystems and certain wildlife, such as salmon in the Pacific Northwest. And petroleum hydrocarbons can have toxicity issues and can be carcinogenic in certain forms that we need to worry about. But across almost all the pollutants, the dissolved phase of these pollutants are generally more bioavailable. They're more accessible to the ecosystem and can have a larger impact to the ecosystem. So we have to be very cognizant of our impacts when we're creating these urban systems and how we manage the runoff from that system. And that's why over the years and decades really, we've developed stormwater treatment practices. And I like to call them stormwater treatment practices because that's what they do, but there are a number of names that these go by. BMPs, or best management practices. They're also called stormwater control measures, or SCMs. We've seen SUDS and WSUD in Europe and in Australia. And in US, we also use LID, low impact development, and GI, or green infrastructure, to describe these practices. But we see these practices throughout our landscapes because we've been using them to treat water really since the late 70s, mid 70s to late 70s. So we have decades of experience with things like dry detention ponds, wet retention ponds, infiltration basins. We've more recently constructed wetlands and rain gardens to help improve how we treat stormwater runoff. So the first practice I'm going to talk about, and this is kind of a spotlight on one of our research projects, is permeable pavement. But we were coming at it from the aspect of road salt reduction, and you'll see why in just a few slides. Before I talk about the work, though, I do want to acknowledge not only the partners that worked on the project. We have a number of people at St. Anthony Falls Laboratory that helped with the research. We also partnered with the city of Robbinsdale, the city of Shoreview, and MnRoad, which is a research facility as part of the Minnesota Department of Transportation, as well as many other cities and organizations that helped contribute to the project, and the funding agencies, MnDOT and the Local Road Research Board. So permeable pavement is simply a replacement for conventional pavement. And permeable pavements simply allow the water to flow through the pavement as opposed to forcing it to run off the sides. And they do that by just changing the mix. They remove most of the fines from the aggregate to allow permeability in the pavement. And there are many benefits of permeable pavement. There's runoff volume reduction. So obviously if the water can soak through the pavement instead of running off, you have less moving off the surface. We generally have improved water quality, again, because less water runs off. But because there's less water on the surface of the pavement, we also have less hydroplaning and less spray. And we can see an evidence of spray here in the photos on the right of this slide. The top slide is a conventional impermeable asphalt, and the bottom slide, or the bottom photo, is a permeable surface layer. And you can see with the same truck under the same conditions, we have a lot less spray on the permeable pavement. We also have a smoother riding surface and noise reduction by incorporating some permeable pavements. What we wanted to ask and try to find the answer for is there less winter road salt application on a permeable pavement compared to a conventional pavement? This was built upon a little bit of previous work before our project. So Wenck Associates, located here in Minnesota, and the city of Robbinsdale partnered on a pilot project where they installed some permeable asphalt on some residential streets. And it was a relatively short section, about 100 meters in length total, on several different streets. And they wanted to compare it against directly adjacent impermeable pavement. Now this photo shows in the background the permeable section having very little snow and ice on the surface. And in the foreground, the conventional or impermeable asphalt that is not salted has a lot more snow and ice on the surface. While this is very interesting and very useful, it's hard to quantify the benefits with this. What percent improvement or what percent in salt application do we get from this? We also don't know, is this coincidental? Is this an occurrence that happens often? Or will we just happen to be here at the exact right conditions? So we also looked at some temperature data that was collected throughout the profile of the pavement. And this is going from about a ½ inch below the surface, in this case down to about 18 inches below the surface. And there's two plots. The one on the left is the impermeable asphalt, and this is plotting the temperature profiles from the surface down to depth. On the right side is the same section of time from January 10th to about January 30th of 2012 with the permeable asphalt on the right. And I just want to highlight a few keys. When the surface temperature is warm, the permeable pavement surface is warmer. And when the surface temperature is cold, the permeable pavement temperature is actually colder. So the permeable pavement actually has a larger gradient or a larger change in temperature over time compared to a conventional pavement. But not only that, if we look at the profile and the temperature gradient within the media, not only the pavement, but the porous subbase below the pavement, we also see a larger temperature gradient on the permeable pavement by a considerable amount, even only to a depth of 18 inches. So this, combined with the data on the previous slide, demonstrates that these permeable pavements are insulating. If I can get the animations to go. There we go. So the permeable pavements are insulating. They are preventing heat transfer through the system, not only from the surface down into the sublayers, but also heat from down below up to the surface. So these permeable pavements do act thermally different in addition to all the other water quality and volume reduction benefits. But do they provide more friction? Do they provide more safety at the surface for drivers when we do not apply salt to our permeable pavements? And actually, I should mention, the restriction of not applying salt on permeable pavements is pretty standard. We understand that the permeability of the pavements creates a direct connection between the surface and groundwater. And we are trying to minimize how much salt is getting to our groundwater, so we do not salt our permeable pavements. And we wanted to understand, is there more traction? Is there less snow and ice cover on permeable pavements? To do that, we used a small, portable, push-behind friction tester, which you can see here. It's called the T2Go. And essentially all we do is we set up a grid or a system, and we run transects where we measure the friction on both a permeable and an immediately adjacent impermeable pavement. In this photo, you can actually see this is a block paver system that is a permeable pavement, in which the gaps between the blocks are the permeable areas. The blocks themselves are actually not permeable, but it was immediately adjacent to an impermeable conventional concrete system. So some data from that is this was an example of an experiment we did. We actually wanted to go out and apply some water to the surface and measure the response under conditions where it was below freezing. So we applied liquid water to a frozen pavement while the temperature was below zero and found that there was less ice that formed on the surface of the permeable pavement on the left compared to the impermeable pavement on the right of this slide. In the heat map that you can see in the center, it's actually not a heat map for temperature, it's a heat map for friction. And our friction coefficient, when it gets down to about below 0.35, is when we should start taking caution on the pavement surface. And when it's below 0.25 is actually considered dangerous for pedestrian travel. In my figure, 0.3 friction coefficient is the beginning or the transition between green and blue. And so all of the light blue areas that you see on these two maps are actually where we're getting close to and even going into that dangerous section of pedestrian traffic. And we can see from that we have more ice on the surface on the impermeable, which also corresponds to the photo. Another example of some of the results, in this case, I'm actually showing the friction as line charts, and I'm putting those two criteria, that 0.35 friction coefficient and 0.25 friction coefficient, on this graph as lines, as dashed lines. And we can see on both of these surfaces, in this case, the top graph and photo are the impermeable pavement, the bottom graph and photo are the permeable pavement. We can see many instances where the friction does get down below 0.35 and even 0.25 for a friction coefficient. And from the photos, we can see how much snow and ice is on the surface. Now, overall, we do have information, and we aggregated this data into a score or a value for these different sections. And that's all in the final report. But in general, looking at the surface, I'm sorry, was there a question or something? No, okay. In general, we found that the impermeable pavement actually had more friction than the permeable pavement for this case. And the pictures show the story. There's more snow and ice on the permeable pavement. However, what we also noticed on the impermeable pavement was meltwater pooling. This particular day, the daily air temperature at the high temperature was above freezing, but the low temperature was below freezing. And so we would have snow and ice melt during the day, but then refreeze at night. And so on the permeable pavement, there was no pooling of melted water. But on the impermeable pavement, there was. And so I would imagine the next day, if we had come out and do measurements at the same exact site, early in the morning, we would have been able to capture and measure that pooled meltwater being refrozen. So from that, we kind of concluded that permeable pavements and porous subbase beneath them are not only functioning as thermal insulators, but that is the primary benefit, is to provide release of the meltwater into the pavement and down to the subbase below. I didn't get to show it today in the slides, but we also found that if you had clogged permeable pavements, whether they were clogged with sediment or the pores collapsed, you didn't get the benefits because the surface is essentially still impermeable. Regardless of the thermal properties, you didn't get the benefits of the permeable pavement because the meltwater infiltrating through that permeable pavement is the primary winter benefit because it prevents this case of refreezing. The next project I want to talk about is a project we're calling Biofiltration Media Optimization. And it's kind of a big title. It's a short title with only a few words, but it can be kind of hard to understand. And I need to define what biofiltration is, but I also want to acknowledge the project team. So we have a number of people working on this project from different departments, as well as many partners from industry. And that was actually a very important part of this particular project, and several of our projects, is input that we get from watershed districts, from state agencies, from cities, and from the consultants. And we're very thankful to work with them on a lot of these projects. But what is biofiltration? Well, many of you have probably seen rain gardens or bioretention practices, either in the news or perhaps in your neighborhoods. But what these are shallow depressions that capture stormwater runoff and soak the water into the ground. A biofiltration practice is a specific type of rain garden or bioretention that has an underdrain system, because likely the soils underneath are either shallow bedrock, high groundwater, possibly tight soils like C and D soils that don't allow a lot of infiltration. So in these cases, we have to install an underdrain to capture that water. It still gets filtered in the practice, but it does go to an underdrain and eventually goes back to surface waters. So that's what biofiltration is. The challenge here is that the most common designs incorporate organic material into the media. The engineered media is a mix of sand and typically compost. But many composts, because they're organic and because they are biodegrading naturally, can release a lot of phosphorus and phosphate. And so in an underdrain system like this, it can deliver a lot of soluble phosphorus directly to our surface waters, which is exactly the opposite of what we're trying to do with pollution reduction. So stormwater comes into the system, moves through the media to the underdrains. We have a number of processes, including filtration at the surface in the media. We have vegetation and vegetative processes, and we also have soil microbiology in the rhizosphere, in the area around the roots. But P release or phosphorus release can be a big challenge. Slow filtration rates can be a big challenge, and that can all lead to poor vegetation. So we designed some mesocosm experiments to test some of the media and determine which ones release phosphorus, which ones do not, if any of them have variability in the filtration rate, and what does the vegetation look like in these different mixes. In this case, the primary purpose or primary objective is that phosphorus release. Does it capture phosphorus, remove phosphorus from the water, or does it release it? We looked at a number of different mixes. We looked at two different kinds of compost, both food residue and leaf compost. We looked at peat, sphagnum peat, and reed sedge peat. And the percentages I'm marking here are the percentages in the mix. So for example, we did a set of mesocosms where we had 10% food residue compost with C33 concrete sand, which is the typical sand material in these engineered medias. We also did mixes with 10% leaf compost. We did 20% food residue, 20% leaf, and so on. The base material here, though, is that clean concrete sand, which we do have replicates of just sand with no additional media. So the organics were compost and peat. The inorganics, we included a series with biochar at 15%. And biochar is kind of a big buzzword in the urban stormwater management industry right now. So we wanted to test, what does biochar do in this realm? Can it benefit or does it hurt us? We looked at iron as a media amendment. I had 5% iron mixed in with 20% leaf compost because that's a standard iron enhanced sand mix. We look at iron because at the University of Minnesota, we've done a lot of research on iron amended medias, specifically removing phosphorus. So we wanted to see, could the iron overcome any phosphorus that's maybe being leached out of the leaf compost? And we also looked at spent lime. Spent lime is a waste product from water treatment. It's typically from lime softening of water. And so there's actually a plant here in St. Paul that generates about $1 million worth of waste spent lime every year. And so if we could use that material to capture phosphate, we can have a dual purpose. We reduce waste and we improve water quality. Some of the interim reports or projects and results from this project. This is an ongoing project. Phase 1 is actually wrapping up very quickly, but phase 2 is funded and has already started. Last summer, this is the summer of 2019, we collected data from about the middle of July all the way through almost the end of October. The black solid line is the temperature over time. The blue histogram marks at the top are columns are the precipitation in daily amounts, and that's reported in millimeters on the right side of this graph. The vertical lines, the red dashed lines, the red dot lines, are all of our synthetic events. We filled buckets, I can show this on the previous slide, we filled buckets hanging above our mesocosms with water that was spiked with a very specific amount of phosphorus. We then released that, allowed it to flow through the media, and captured it as it came out of the bottom of the mesocosms. And so every time we did that is a red dot line, vertical line, and a numbered line on this graph. And you can see we did it almost every week all summer last year. The red dotted lines that are highlighted yellow are events in which we took the samples and also analyzed them for nitrogen in addition to phosphorus. So that's kind of the context of the experiments. We've continued these experiments in this summer, and we have a lot of that data, although it's not ready to present yet, and we will continue that for the next 2 summers, summer of 21 and the summer of 22. But of the criteria we wanted to test, filtration rate was one criteria. We want to ensure that the water flows through this media quickly, because if it has a slow filtration rate, we can't treat nearly as much runoff as we want. This graph, and I just realized that on this slide, the axes don't show up very dark, so they may be hard to read, but on the vertical axis is the mass of water coming out of the system. The solid black line is the volume that we put into the system. So you can see that it very quickly rises to about 75 to 80% of the influent volume within about the first 20 minutes. The horizontal axis here is in minutes, and the 20-minute mark, if you can see my cursor, is right about here. So you can see we get to kind of our plateau within about the first 20 minutes. And then over the next hour and a half or 2 hours, another 5 to 10% of the volume comes out. Now, why don't we get all of the water back? Well, this is a porous system. This is a system with organics in it, and it's a system with vegetation. So we have evapotranspiration coming out of our mesocosms because they are outside. And so there is some pore capacity for holding water even when we're doing these experiments. But overall, most of the mixes performed very similarly. We have very fast release of the water very quickly, and then a slow release of some of the excess. When we talk about phosphorus concentration and pollution, this is data that is demonstrating the effluent phosphorus concentration on the vertical axis. And on the horizontal axis, we have the different events, the 14 events that we did last year. But these are grouped now by media so that you can see how different mixes compare to each other. On the far right side, we have the tank concentration, which varied a little bit over the summer, but on average, I have it marked here with a red line. That's the average influent coming into our mesocosms. So any effluent phosphorus concentration that is above this line is phosphorus release. Any effluent concentration below the line is phosphorus capture. And I can highlight the ones or the media that released phosphorus, that had more phosphorus in the effluent than what came in. And so things like food and leaf-based compost, biochar actually released a lot of phosphorus, or at least it did not mitigate the phosphorus that was coming out of the 20% leaf compost that was in the mix with the biochar. And the spent lime also released phosphorus compared to the influent concentration. By comparison, the iron amended sand and the reed sedge and sphagnum peats did not release, and in fact reduced the amount of phosphate that came out of the system. Even our control columns here, the sand mesocosms, has some capture of phosphate throughout the year. And we've actually seen that in previous experiments with iron enhanced sand. Plain sand can have a little bit of capacity in the beginning of its life, simply because it does have some calcium components in it. And so it will capture some phosphorus, but we could see even towards the end of the year, it was already getting to its full capacity. In phase 2, which we've now begun, we will extend our experiments to be a multi-year performance evaluation. We will also incorporate the impacts of road salt. So next spring, we plan to dose these mesocosms with a dose of road salt to see if we release or mobilize a bunch of phosphate from these experiments, even in the ones that captured phosphate last year. We will also be running an experiment where we test low organic content mixes and things even as low as 1% organic matter. And then from all of this, we will be developing some guidance and training, because a main component of all of these projects is to get the information back to practitioners so that they can make changes in their designs in how we manage stormwater runoff in the real world. So the last area I want to talk about is iron enhanced sand filters. And as I kind of mentioned earlier, this is something that we've been doing a lot of work on really for the last 10 to 15 years. So we have data from not only laboratory experiments, but a lot of data from actual urban and agricultural full-scale installations that have been in the ground for now over 10 years. Again, we have a number of collaborators. I work very closely with Professor John Gulliver here at the University of Minnesota. We also invite Professor Pete Weiss from Valparaiso University to come and work with us. And he works with us every summer on our projects. It's also interesting to note, Pete also grew up in Houghton and is also a Michigan Tech alum. So it's good to make that connection with him, although he was there at a different time than I was. We also have, as I mentioned on previous slide, a number of staff and undergraduates that work on these projects, as well as funding agencies, both from state agencies, such as MPCA, our Minnesota Pollution Control Agency, our MnDOT, our local road research board, but also cities, watershed districts, and counties that not only work with us in finding sites and working on projects, but also providing some funding in some cases. But this project and this concept comes from the idea of sand filtration. And actually, as a civilization, we've been using sand filtration for thousands of years to treat water. And so it's not a new technology, but we know that it's a high-performing concept and practice. We can remove 80% or more of particulates with a sand filter. We wanted to amend a sand filter with something to also capture the soluble phosphate. And what we found by evaluating a number of different amendments or enhancements was that granular iron actually works very well. We can absorb phosphate ions onto a oxidized iron particle, and we can capture a lot of phosphorus with that. In the laboratory, we showed here, this is a box and whisker plot showing where on the left, we have the phosphate concentration. And for the influent, we had an average of a little over 300 micrograms per liter coming in. Our 100% sand basically didn't remove anything within the margin of error, but adding just 0.3% iron by weight, a relatively small fraction, less than 0.5%, we captured almost 20% of the phosphate. When we went to 2% and 5% iron by weight, we got upwards of almost 80 and almost 90% capture of just the soluble phase of phosphate in the water. And so that was very encouraging from the laboratory perspective. But then taking that into the field, we need to understand how do these practices work in the real world environment, when there's competition with other ions, when we have changing water chemistry, when we have varying amounts of phosphate in the influent. This is an urban installation of a surface sand filter that is amended with 5% iron by weight. This practice is one of the oldest that we know in Minnesota. This is in Maplewood, Minnesota, and it captures runoff from about 8 acres of an urban drainage area, and this is about 1/4 of an acre in size, the filter itself. This has been monitored by the local watershed district for a number of years. And these plots are, again, box and whisker plots that are showing phosphorus, but in this case, I'm showing both total phosphorus, TP on the left, and soluble phosphorus, soluble reactive phosphorus on the right. So for total phosphorus, we see a 75% reduction in the real world, which is really good. Soluble phase, we're seeing only about 44% reduction. But it's important to note that the limits of detection for our analytical methods are actually this red bar, this 10 micrograms per liter. About 2/3 of the samples are actually below detection limits. So we use 1/2 of the detection limit in the calculation, which is why we'd only get about a 44% reduction. But the effluent water quality out of this system, and I can show you again with my cursor, for total phosphorus, we're down at about 25 micrograms per liter. And for reference, all of our water quality targets in Minnesota generally are on the order of 40 micrograms per liter, or 60 or maybe even 90 micrograms per liter. So the water quality coming out of this system is much better than the water quality criteria and target we're trying to hit in our surface water. So it's performing very well. But agricultural runoff can also be an issue. And this is a full-scale system that was installed downstream of a tile-drained agricultural field, which is a mix of pasture land and row crop agriculture. This was also monitored actually through a project at the University of Minnesota in St. Anthony Falls lab over 3 years. For total phosphorus, we saw about a 66% reduction in the total phosphorus concentration and about a 64% reduction in the soluble phosphorus concentration. And again, very good water quality coming out. Our average here is on the order of 50 micrograms per liter for the soluble phase. And for reference, the downstream lake in this particular case, the target is 60. So we're meeting our goals. Another urban example is actually a retrofit. So the first two examples I showed are new construction. This is a retrofit concept where you would take an existing wet pond, which you should see on the right side of your slide here, and we install a trench along the perimeter that is an iron enhanced sand, such that when it rains, water comes into this pond, the water level increases and is forced to flow into the filter trench to an underdrain before it can actually flow out of the pond through the overflow structure. We did some initial testing on this type of practice way back in 2010 when it was very first installed. And that testing actually showed very good performance. Again, about a 73% reduction, in this case, in the soluble reactive phosphorus concentration. But coming back 3 to 5 years later, we found that the performance was not nearly as good. We saw actually about only a 26% reduction in the phosphorus concentration. And we realized in going out and doing this study and talking with the city and doing some inspections and testing, we found that this practice needed maintenance. The problem with this system is it was remaining saturated for long periods of time. And under those saturated conditions, the water can very quickly become anaerobic, especially in these iron-rich type soils. And so we saw anaerobic conditions, we saw poor performance, and that was what was causing this need for maintenance. So we went in, we improved, we raked the surface, we improved the hydraulic performance of the system to allow the water to drain out more quickly. And the following year, we saw an increase up to 43% reduction, up from 26%. However, that's still less than ideal. We're only capturing less than half of the phosphate. And so the other thing we learned from this is a sense of the lifespan. If you put too much water through these systems, they will eventually run out of capacity. And so we have good numbers now from both our laboratory experiments for capacity and some of these field monitoring studies on the lifespan and capacity of these systems. And so when we compare all of those, there's really different metrics. The first metric we've been using is what's called the estimated treated depth. And the treated depth is simply if you take all of the water that flowed into the system and stacked it on top of itself, right? Accumulated all of that water over history, that is the total treated depth, or the estimated treated depth. And we can see for these pond perimeter trenches, we've had nearly 550 meters of treated depth at the time we did monitoring, which explains why we only had 43% capture. On our laboratory experiments, we did up to 200, a little under 200 meters of treated depth. And on our agricultural, we had almost 300 meters of treated depth. And we can see the gradual decrease in load captured of phosphate because of that over time lifespan and longevity being using that phosphate absorbing capacity. We also have some numbers here of comparative influent concentrations and the influent mass. And we're still trying to understand all the variables with this, but now I think we have some good sense of why these things start to lose their capacity and their efficiency over time. I also need to mention, though, that not all iron is created equal. We found that many suppliers were trying to suggest, well, can we use this iron or can we use that iron in these iron enhanced systems? Some waste products have only 30% iron in them. And so they're going to be less effective than a more pure cast iron source material. And in the ones that have less iron, there's going to be more impurities. We could have metals that could be harmful or toxic. We could have lubricants if it's coming from a metalworking or fabrication shop. The materials could also have other adverse effects. There's been several studies on slag that comes out of steel manufacturing. And while it is great for sorbing phosphate, it's one of the things we tested in the early days, it can also increase the pH of the water to levels of 10 or even 11, which you'll remove the phosphorus, but you'll also kill everything else that's in the water, right? You also need an iron that's reactive. We found some materials that are iron, high purity, low impurities. They don't have these adverse effects, but they're non-reactive. They have some kind of coating in the elemental structure that's preventing phosphate from being absorbed. And of course, particle size, you want to be in the right size range. So that's kind of a summary of our research. We do a lot more research. If you're interested in any of the work that we're doing or want to hear about new projects, I encourage you to check out Stormwater Updates. It's an email newsletter, as was mentioned in my introduction. We talk about our stormwater research that's across the University of Minnesota, and you can sign up at stormwater.safl.umn.edu. You can also find past issues. You can find links to journal articles and project reports and graduate theses if you want to see work related to stormwater research that we're doing. And the last plug I will say is about the Minnesota Stormwater Seminar Series. This is a seminar series that we started last year in 2019 with the concept of bringing nationally recognized experts in stormwater innovation and green infrastructure knowledge to Minnesota to give a keynote lecture. And these are the kind of people that would be giving keynote lectures at conferences, at stormwater conferences. And then we would put that keynote speaker, that expert, on a panel with 3 local experts on that particular topic and have an extended Q&A discussion. And this has been a very popular, very successful seminar series. We have continued it into the COVID conditions. We are now fully remote. Previously, we were in person and streaming live and recording. Now we are streaming live and recording without the in-person component. But you can see we've had a number of great experts, well known in the stormwater industry, nationally and worldwide, really. And you can see previous recordings if you're interested on our YouTube channel, which is linked here, or simply searching for Minnesota Stormwater Seminar Series. You can see all of the past events that we've had, and you can sign up for updates to get announcements of new events, and also visit the Stormwater Seminar Series website, again, linked here on this page. So with that, I will thank you very much for your attention, and depending on how much time we have, I'd be happy to answer any questions you may have. Thank you.
Yeah, we have a few minutes, and then if people want to stay a little bit longer, we can keep Andy on the line too. But first of all, just we have a virtual round of applause. We can't really applaud, but I'm sure we all thank you very much, Andy, for your great talk. Any questions from the audience for Andy?
I like the round of applause. Thank you.
Yeah. Well, I have a question while the others are thinking. So on the permeable pavement, one thing I've heard is that it can be a little bit weaker. So for big trucks, and especially going fast, it may not hold up as well as normal pavement. What's your thoughts on that?
Yeah, that's a great question. It's actually a common question that comes up. Permeable pavements are still relatively new, right, in the pavement industry and the pavement history. And so we are still developing and still improving. And for sure, the best applications for these permeable pavements are residential areas, residential streets, parking lots, driveways, things like that. They are really just not ready for the high traffic, high speed conditions of interstates and highways. But there is more and more improvements every year. Like I said, Minnesota Department of Transportation has a low volume road section, which is more of a low traffic, low speed test section. And they've done a number of different permeable pavement mixes there and improved the designs. But they also have a high speed section that's a chunk of highway or Interstate 94 in Minnesota, where to my knowledge, they haven't tested permeable pavements on that section yet, because I think they already know that it just can't hold up in terms of the durability. I will say though also, especially in areas where permeable pavements are new, there is a learning curve to installing permeable pavements. And especially in cold climates like in Minnesota, there was a lot of hesitation because we were worried about freeze thaw and frost heave. But the state of New Hampshire, and specifically the University of New Hampshire, has done a lot of research of permeable pavements in cold climates. And they've come up with a lot of very, very good specifications, design drawings, and criteria for how to do permeable pavements properly, both for cold and warm climates. So there is knowledge out there. We can build it, but a lot of contractors might need more hand-holding and more input when they're just learning how to build these from scratch in the beginning to make them successful.
Yeah, and then clogging too. We put a lot of sand on our roads, and that sand can clog all the pore spaces sometimes as well. So.
Yeah, absolutely. We saw evidence of that. Again, I didn't get to show any slides on that here today, but we found evidence of that. We've measured some of that. There actually is a really good paper, and there's some good recommendations I can share with anybody that needs them. There's some really good maintenance findings and research on how to properly maintain these permeable pavements. In general, though, vacuum sweeping is the best method. You absolutely should not use a broom sweeper because that tends to drive the particles further into the pores and make it harder to remove them. So you want a nice vacuum sweeper to remove particles from these surfaces.
Let's open up to the students. Students, any questions for Andy? All right, students are still thinking, apparently. I got one more. So when you enhance with the iron, I think it's a great idea. Is there any way to regenerate that iron after a period of time to either, I don't know what you would do to regenerate it so that you keep it useful more for a longer time period?
That's another good question, and we get asked that one too. It's so regenerating the iron can be challenging. So the iron itself, it's a granular media. We generally try to get it in the same size range that the sand is, so we don't have any migration. We also want it to be generally small, just so that it has more surface area per mass, right? So that iron surface will rust over time. It'll oxidize over time. And actually, parts of the iron, it will break off. It'll fall apart. We can see some of that in the effluent. We can see some of that on the outlet structures. We can see some of the iron coming out. So it's actually naturally kind of degrading and removing it. Now, we did test the iron that comes out in the effluent, and there's A, very, very little iron that comes out. B, there is some phosphorus on that iron, but it's bound very, very strongly to the iron and does not want to come off under, unless you have some very, very, very specific kind of conditions, which we wouldn't see in the natural environment, other than anoxia. Although, again, some of the other research we don't get to talk about. We're doing a lot of work right now with ponds, stormwater ponds, and releasing phosphorus. And we've seen that even if you put iron at the bottom of a stormwater pond that is anoxic much of the year, if not all year, the iron can actually hold on to the phosphate even under those conditions, which is really interesting and counter the conventional wisdom. So, but rejuvenating it, generally we've shown that even 5% iron can last 20 years or more in some cases. These pond perimeter trenches, which was a new kind of technology, they are overloading it. And so maybe only 5 to 10 years. And there's not really a way to rejuvenate. But what we'd like to see is that material actually removed and then sent back to the manufacturing and maybe recast. So maybe refurbished, if you want to think of it that way. Looks like we have, I see a question in the chat. Do you want me to just read questions from the chat, or did you want to ask them?
No, you can go ahead, and then I see Kenny Larson has his hand up too. So
I saw that. Why don't we take the raised hand question first?
Yeah, go for it.
First off, thanks for your presentation, Andy. I really appreciated it.
Yeah, my pleasure.
I just had a question about some of the stormwater ponds where, especially the one where you had the trench. What was the interval with which you were looking at phosphorus output from those ponds? With what regularity? Was it seasonal? Was it like weekly?
Yeah, very good question. So we did those pond perimeter trenches was actually part of 2 different projects. And so we had some testing phase where we went out and we actually dosed the water with fire hydrant water. And so we controlled those. We did those during dry weather. We conducted several tests over the course of probably 2 months. Okay, so that was several different events over about 2-month time period, the first year after they were installed. But then we also monitored other trenches in the same city, and monitoring was actually every time we had a rain event. So if we had a rain event really over about 1/4 of an inch of rainfall, we would have automatic samples collected, and then we'd go out, retrieve the samples, and analyze those. So we would get a number of events all summer long for 3 summers at that particular site. And it could be weekly, it could be a couple times a week. Certainly during certain times of the year, we went almost a whole month without any rain, just because of the natural rainfall, but that was the frequency.
Thank you.
Yeah. So this other question in the chat, what's the average lifespan of these impermeable pavements in cold versus warm regions, or permeable pavements, right, in both cases? What we've seen is the ones that, I'll say in general, permeable pavements so far, again, being relatively new, we don't have necessarily a long history of permeable pavements and total lifespan, but so far, most permeable pavements if designed properly and installed properly, can last as long as, or at least nearly as long as, a conventional pavement of the same type. Again, there's some caveats there. There are cases where permeable pavements fail, and oftentimes that's because it was a poor installation or poor possible design criteria. They had to go in and redo it. But generally, it's on the same order of magnitude as a conventional pavement. But again, only in these low traffic, low load, relative low load capacities for residential streets and driveways and parking lots. Looks like we have a couple other raised hands. Can you call on them? So
I see Eric Seegren has a hand up. Go ahead, Eric.
Sorry, I had to unmute myself. Yeah, nice presentation, Andy.
Thank you.
I was wondering if with your work with iron, had you experimented with iron-coated sands at all?
So we've done granular iron. We have not looked at coated sand, although I know that's out there. I know there's companies that do iron-coated sand, and there's actually a lot of companies that are coating materials like zeolite, right, and high permeable materials with various coatings. We have not tested any iron-coated sand, although after these are installed and in place for a year, the sand is pretty much iron-coated at that point, just because of all the iron that's there and the mobility of it within the media itself.
Right.
It ends up coating all of the sand.
Okay. All right.
Good question, though. There was another raised hand, maybe?
I don't see any at the moment, but go ahead, anybody who wants to.
And obviously, for future reference, if you have any other questions or would like any other links or resources or publications, or wherever we publish some of this work, my email is here for that purpose. So you can obviously contact me anytime. I'm happy to chat and answer questions.
Yeah, well, thanks, Andy. I appreciate your time and talking to us. It's been really interesting. We teach a course on stormwater low impact development, so I can take this back to them.
Great.
And tell the students, and maybe once the whole virus thing settles down, maybe we can come visit or something.
That would be great. I'd love to come back up there again too. And anytime anybody is in the cities, if you would like to see St. Anthony Falls Lab, University of Minnesota, and any of the work that we're doing, again, save my email, send me an email. I'd love to give tours and talk about the research, not only that we're doing, but that we're doing at St. Anthony Falls in general. We're happy to take visitors and give tours. So anytime.
Yeah, I'll say that's a sister lab to where I went at University of Iowa's Hydraulics Institute, and so there was a lot of collaboration there. So
Yep.
really two very good institutions that you students could consider for further graduate studies after this or whatever.
Mm-hmm.
All right, well, thanks everybody. I think we'll end it here, and have a great day. And Andy, thanks again. I really appreciate it.
My pleasure. Thank you so much for having me.
Yep. All
Hey,
right.
Brian, really quickly, if anybody would like documentation for PE continuing education credits for this or last couple seminars, let me know.
Yeah, great. Thanks, Eric. Really appreciate that. All right. Bye, everybody.
Thanks, Andy. Good seeing you.
Thanks, Professor Watkins. Thanks for joining. Good to see you.
You're welcome.
How you been?
So pretty good.
Good.
Yep. Just I have to hop on another call right now, but yep, might take you up on your